Hello and welcome. In this video we are going to explore how to use matrices in dynamic modeling. Our story starts over 800 years ago when a mathematician named Leonardo from Pisa, Italy was curious about how fast a rabbit population would grow. He proposed a simple, albeit unrealistic model. Leonardo built his model around pairs of breeding animals, rabbits. An adult pair would produce a juvenile pair of rabbits every month. Each juvenile pair would take 1 month to mature, at which it would join the ranks of reproducing rabbits. Death was not included in his model. Now we would start our dynamic model following these rules with an initial condition consisting of a single pair of adult rabbits. After a month, that pair would produce 1 pair of juveniles. After another month, the original pair would produce another juvenile pair, and the original juvenile pair has now matured to be counted as an adult pair. In the 4th month, the 2 adult pairs have each produced a pair of juveniles, and the previous juveniles are now adults. By the 5th month, there are 3 juvenile pairs coming from the previously mature 3 pair of adult rabbits, and 5 adult pairs consisting of the prior 3 adult pairs and the 2 now mature pairs that were born last month. Once we have an understanding of the dynamics governed by our model's rules, we begin the process of modeling the dynamics with mathematical equations. And the first step in modeling is to consider the variables for our system. In each month, our system is completely characterized by knowing the number of pairs of adults and juvenile rabbits. We let A represent the number of pairs of adult rabbits, and let J represent the number of pairs of juvenile rabbits. And because the numbers change each month, we actually have a sequence of values. If we let T represent which month is being considered, then A sub T and J sub T will be the values for A and J corresponding to month T. Because the state of our system each month is characterized by multiple values, we will actually create a sequence of state vectors, each of which contains the values of our state variables. The state vector x sub t will consist of A sub t and J sub t. So now we can go through each of the months. In the first month, we can see that we had 1 pair of adults and no juveniles. In the second month, we had 1 adult, 1 juvenile, so our vector was 1, 1. In month 3, we have 2 adults and 1 juvenile pair, so our vector is 2, 1. In month 4, we have 3 adults and 2 juveniles, and so our state vector is 3, 2. And in month 5, our state vector is 5, 3. If we look at the sequence of values corresponding to the number of adult pairs, we see the values 1, 1, 2, 3, and 5. These are the first 5 values of a famous sequence. We now refer to Leonardo and the sequence he discovered by another name. That name is Fibonacci. Maybe you've heard of the Fibonacci sequence. At the time of Fibonacci's discovery of this sequence, matrices had not been invented. We, on the other hand, are studying matrices. Fibonacci's model can be stated in the language of linear algebra, so we began a discussion of how that might proceed. A mathematical model for dynamics is characterized by an equation for how we can determine future values based on the present and past. We start by considering the number of adult pairs. From any given month, the pairs of adults in the following month will consist of those already adults, as well as the juveniles that will have matured. This gives us an equation. The number of adults in the subsequent month will equal the sum of the number of adults and juveniles in the current month. In other words, A for the next month, t plus 1, will be equal to A sub t, the number of adults in this month, plus J sub t, the number of juveniles this month. Now, in addition, only the pair of rabbits that are presently adults will reproduce, and so we get an equation for the number of juveniles as well. The number of juveniles in the next month, J sub t plus 1, will equal the number of adult pairs in the current month, A sub t. Linear algebra can be used to understand our model because each of these equations are linear combinations in the state variables. So if we consider a state vector for the next month, x for t plus 1, then we can think of it as a linear combination of vectors. I've got a sub t times the vector 1, 1 plus j sub t times the vector 1, 0. Well, we have a linear combination of vectors, and so we can write that as a matrix, the matrix being 1, 1, 1, 0, times our current state vector, a sub t, j sub t. We now have our dynamic model as an iterative matrix multiplication. What I mean by that is that given any state vector, that's x sub t, the next state vector, x sub t plus 1, can be computed by multiplying the matrix M times x sub t. In biological models for populations, the matrix M is called the projection matrix because it is used to project the population state into the future. So now, we've been learning about eigenvectors and eigenvalues, and we want to start by thinking about how would I analyze this model in the language of our eigenvalues and eigenvectors. So the first step in our eigenanalysis is to find the eigenvalues, and we do that by first defining our characteristic polynomial. So our polynomial is equal to the determinant of lambda times the identity matrix minus R matrix. And so if I take a lambda on the diagonal and subtract my matrix, I get this new matrix, lambda minus 1, minus 1, minus 1, and lambda. When I calculate the determinant of that, it's a polynomial, lambda squared minus lambda minus 1. We find the characteristic values by finding the roots of this polynomial. Because p, our polynomial, is quadratic, we can find our solutions using the quadratic equation. So here, I like to sing the song, x equals negative b plus or minus square root b squared minus 4ac all over 2a. But here it's lambda. Our value for the coefficient b in the quadratic is negative 1. So negative b is plus 1. Plus or minus the square root of that negative 1 squared, that's b squared, minus 4 times a, which is 1, times c, which is negative 1, all over 2a, which is 2 times 1. The value inside the radical is just 5, and so I have two eigenvalues. My first eigenvalue is 1 plus the square root of 5 all over 2, and my second eigenvalue is 1 minus square root of 5 all over 2. To find my eigenvectors, which are going to be basis vectors for the eigenspaces, we're going to look at the null space of the matrix lambda I minus m. Now we know that for the two values of lambda, this matrix is singular. In other words, when I go to a reduced row echelon form, one of the rows will be all zeros. And so if I look at the second row of the original matrix, minus 1 lambda, put that in the first row and change the sign, I know that this is my reduced row echelon form. I can now solve for the null space. I think of my juvenile variable, the second variable, as free. The first variable is now equal to lambda times the juvenile variable. And so if I choose my juvenile value to be 1, notice that my eigenvectors, the basis for each eigenspace, can be written as just the eigenvalue in the first value, in the adult spot, and 1 in the second spot, the juvenile. So here are my eigenvectors. Well, we have two eigenvectors. We can see that they're linearly independent. R2 is a two-dimensional space, and so these two vectors form a basis. We can write our initial value, x1, remember that was one adult pair and no juveniles, must be able to be written as a linear combination of my two eigenvectors. And so I write down the equation. X1, 1, 0, is equal to a constant times v1 plus a constant times v2. And if I write down the augmented matrix for that system, I get a matrix on the left with lambda 1, lambda 2 in the first row and 1, 1 in the second row, augmented by the column 1, 0. So you can go through the process, but to save time, the reduced row echelon form has the identity matrix on the left And the coefficients I discover are C1 must be 1 over the square root of 5, and C2 must be negative 1 over the square root of 5. This means I can write my original state, x1, as 1 over square root of 5 times the first eigenvector minus 1 over square root of 5 times the second eigenvector. This gives me my initial condition, and our iterative equation tells me that the next value of my sequence is equal to a matrix M, remember that was 1, 1, 1, 0, times the previous state. So I can calculate x2. That's M times x1. And if I substitute in place of x1 the formula that I just have in terms of linear combinations of v1 and v2, I get M times that linear combination. The properties of matrix multiplication allow that matrix to distribute, and then the scalars, here they're 1 over the square root of 5, can factor out of the matrix, so that I can write this equation as my x2 is now equal to the scalar 1 over square root of 5 times mv1 minus the scalar 1 over square root of 5 times mv2. Now v1 and v2 were special. They're the eigenvectors. And so m times v1 is just lambda 1 times v1. And m times v2 is lambda 2 times v2. And so I again have a linear combination of v1 and v2, but my scalars are now 1 over the square root of 5 lambda 1 and minus 1 over square root of 5 lambda 2. When I multiply those by my original vectors, I notice that my vectors are seeing increasing powers of lambda 1 and lambda 2. That's because of that scalar multiple. I can repeat this again. x3 is the matrix M times x2. Again, substituting in my linear combination for x2. My matrix M distributes. The scalars, which now are both the 1 over square root of 5 and the lambda value, factor out. So I have 1 over square root of 5 lambda 1, the scalar, times mv1, minus 1 over square root of 5 lambda 2, the scalar again, times mv2. Again, we use the eigenvector property that m times an eigenvector is replaced by lambda times the eigenvector, and I have my expression x3 is now a linear combination of v1 and v2, but now the lambdas are at the power 2. This pattern repeats and repeats and repeats, so that in general, after t months, or the t month vector, I see is 1 over square root of 5 lambda 1 to the t minus 1 power times the first eigenvector minus 1 over square root of 5 lambda 2 to the t minus 1 power times my second eigenvector. And when I multiply those eigenvalues into the vectors v1 and v2, we get a simplified formula. So that if I look at the first value in my vector, the adults, I discover that it's 1 over the square root of 5 times lambda 1 to the power t minus lambda 2 to the power t. And so I get this formula of how my adult population grows. Now what's interesting is we have just developed an explicit formula for Fibonacci numbers. Remember that the adults were my Fibonacci sequence. So if I wanted to know what's the 10th Fibonacci number, I would substitute the value 10 into this formula, I could calculate it, and that would be the 10th value in my sequence. Well, this value, 1 plus the square root of 5 over 2, that eigenvalue lambda 1, has a special name, and that special name is the golden ratio. Now if you want to learn more about it, you can go to Wikipedia and look up Fibonacci sequence. There's lots of interesting properties. But let's summarize what we've learned here in this video in relation to matrices. Recall we started with a dynamic model, and we developed equations where the future values were linear combinations of current values. That allowed us to rewrite the model as a matrix iteration, where my new state vector, x sub t plus 1, could be written as the matrix my projection matrix, times the current state vector x sub t. We then found the eigenvalues and eigenvectors for our matrix, and we could express the initial vector, x1, as a linear combination of our eigenvectors. Once we had that linear combination, we could repeatedly multiply by my matrix, and the effect was my linear combination saw increasing powers of the eigenvalues. So my first eigenvector, as time progressed, I just had repeated multiples of lambda 1. And the second eigenvector, after repeated multiplication by m, saw repeated multiples of lambda 2. Now those repeated multiples, lambda to a power t, is a geometric sequence. And the consequence is, for these dynamic models that were governed by matrix multiplication, every eigenspace sees exponential growth if my eigenvalue happens to be bigger than 1 in size, or exponential decay if my eigenvalue has a value that's less than 1 in size. So here, our Fibonacci numbers are growing geometrically, and helps us understand how this rabbit population that Fibonacci started looking at would have grown.